Spoto from the Observatory of Côte d'Azur in Nice, and the title is Contribution of Gaia to Asteroid Dynamics.
So, good afternoon, thanks for being here. I'm sorry for the inconvenience, but since I have some very good results, so don't sleep all till the end. And first of all, I would like to acknowledge the other authors of the work, of course, which was Paolo Tanga and François Mignard, and all the CU4 team, which is the unit of the Gaia framework which is working on the solar system objects. So Gaia is a NISA mission. It has been launched in December 2013 and it's currently serving the sky for the Lagrangian Point L2. The main goal of Gaia is that it's going to give us the astrometry for stars and asteroids at this 2 millisecond accuracy. I don't know if you are aware of it, but in September 2016, the first Gaia Data Release came out, and it contained 2 million stars with positions and proper motion, and 1.1 billion stars with no proper motion, so just position. Regarding Gaia and asteroid observations, the mission at the end will observe around 300,000 asteroids till few kilometers in diameters. So there will be also comets and TNOs, actually very few TNOs, and then there will be maybe small planetary satellites. Every object at the end of the mission will have almost 70 observations, and mostly there will be many they will be main belt asteroids, and we will have as well some NMAs. How does it work, the asteroid processing for Gaia? We have two kinds of processing. One is the daily processing and the other one is the long term. For the daily processing, we process what we call the new asteroids, which means the asteroids which are supposed to be discovered by Gaia. And the daily processing acts per object, and there is a time frame of 48 hours between when the asteroid is discovered and when the observations are available through a website. It uses a preliminary astrometry and a preliminary calibration. The result is what we call the alert. So when the object is supposed to be new, the observation came out, and then what we want to have, what we would like to have, is the ground-based follow-up. On the other side, for the long-term processing, at the end of the mission, which will last for 5 years, we expect maybe more, we will have all the sources, so all the asteroids that Gaia is going to observe, and it will have the best calibration, the best astrometric model, and what we have will be the astrometry and the photometry and the spectral type for the asteroids. So to do the long-term processing, we need the validation and the refinement of the orbits. So this is the outline of the talk, more or less. The idea is what we can do at the present, or better, what we have done in the past years, and what we will do in the future. So the first Gaia Data Release already came out. The second one will come out in April 2018, and it will contain almost 10,000 asteroids. So I'm going to talk about the next Gaia Data Release. But let's start with the present. So let's see what we can do when we look at the stars and we use the stars from the GDR1. Let's start with the occultation. The occultation in general of a star by an asteroid is when the asteroid passes in front of the stars. So from the Earth you cannot see its light. This is the geometry that you clearly see from the occultation side, because from the Earth you cannot see the star. So what we have done is that we have taken the stars in GDR1 when they had both positions and proper motion. When they had no proper motion, we use the proper motion from other catalogs, other stellar catalogs. And we use the star to re-reduce all the occultation astrometry following this simple geometry that you can see here. And the idea is that at the end we made an orbit determination process using only the occultation. So let me show you the result, and let's start with what we had before Gaia. So this plot represents here, you have the uncertainty on the same imagery axis for each asteroid we processes, and the uncertainty on the same imagery axis represents the quality of the orbit. Here you have the same quantity if we use only the occultation to produce the orbit. So just to give you an idea, the number of occultation will go from 4 to 15, while the number of all the observations available from the Minor Planet Center are around thousands of observations for each asteroid. So this line represents where the two should be equal. So as you can see, everything is towards the upper side of the plot, as you can imagine. But if you are going to use Gaia, so you can use it as a cartoon, you see that everything is going down, and you have still some objects which has an uncertainty on the semi-major axis, which is better just using occultation. This is the color codes for the numbers, so around 10 and 12 occultations. And this is the result which is possible because the accuracy on the stars for Gaia, it's very high. Another effect that this has on the orbit is that this is what we have seen using GBOT. So the Gaia satellite, since we need a great accuracy when we are going to use the stars or the asteroids or the observations, we have to follow the spacecraft with a precision which is very high. That's why they started to have this Gaia-based optical tracking, which makes use of two main telescopes. One which is the Liverpool telescope, which is La Palma, and the other one is the VST Survey telescope, which is called the VLT. And they observe Gaia, but they also observe some asteroids per night. And then they reduce the observation using both the PPM XL catalog, which was one of the best available catalogs before Gaia, and using the GDR1 catalog. So let me show you, have some example. I don't have so many times to show you all the examples, so I will show you just the NEA, which was the first NEA discovered by GBOT. So, as I told you, it was discovered by GBOT in March 2016, and when it was discovered, it was on the impact risk list with a low probability for February 21.2 and 21.6. Then new observation a few weeks later from Mauna Kea, which are very good observation, rule out the impact. But the question is, what would have happened if GDR1 were available at the time? So I've been lucky because Giovanni yesterday told you everything you need to know about the line of variations. But here you have the target plane in the case in which the observation are reduced with Gaia, this one, and this is the observation as it was at the beginning. So if you imagine, this is the lob, the black points represent the lob, and the red point is the Earth. If you link all the points, you see that this line is going through the Earth, and this represents the possible impact into 21.2, while on the other side, what you have is that the line is not passing through the Earth. So then we proved that the orbit was effectively closer to the real final orbit, and we used two different metrics. One is based on an identification algorithm on the lob because the problem was non-linear. And what we find is that it's true that the second orbit, which is the one computed the observation using the reduction by Gaia, it's closer to the final orbit, which is the one who rule out the impact. So if Gaia were available, the object was not on the impact list since the beginning. Then, let's move to the others, which are still the present. What do you have? So follow this line because it's what we will use later when I'm going to talk about the next data release. The idea is that Gaia does not produce images. It has just the position of the asteroid along scan and across scan following this path. So the green boxes are the CCDs, and you have up to 10 CCDs here, and this represents the BPR and RT and RP type, which are for the color code. So this is what I told you. So when Gaia observes an asteroid, then the observations are matched to the catalog of known asteroids. If the observation match, then the idea is that okay, we can add the observation to the known asteroid. Otherwise, it is supposed to be a new discovered asteroid from Gaia. So we have the astrometric reduction, we use the short arc orbit determination, and then we can predict the orbit and how to look for the follow-up from ground. This is one object. I'm going to show you just one object. We have plenty, we have a lot of objects. But this is the one object which was discovered almost by Gaia, and then you will find why. It has 4 Gaia transits. Each transit is made almost by the collection of all the position in each CCD. So at most, each transit can have 10 positions. So what we are going to use is not just 4 positions, but you have, let's say, 10 and something else for the others. So at most, you can have 40 observations for the asteroids. But the time span is very few because each transit is 44 seconds.
Transit of what? Transit.
Each transit is when the object passes through these 10 CCDs. This is called a transit. Each CCD is one observation. So then we use the short-term orbit determination, as Alexio explained very well on Monday, and then we were able to find an orbit. We predict, we follow up the object from the OHP, which is the observatory in Provence, and what we were able to find was that the linkage between the Gaia orbit, which is these are the residuals for the Gaia orbit, and the blue points are the residuals for the OHP. So you can see a few things from this plot. One thing is that the OHP is obviously not that good as an observatory, and Gaia is better, but this is good for us, and we knew that. But on the other side, you can see that there is a correlation between alpha and delta, which is really important when you have to use the error model for the long term if you want to have good residuals and predict the quality of the data. And this is what led me pass through the new Gaia data, the new results of the observations. So the new data release, which will happen in April, will contain a sample from this, as you can see here, this is a plot that François Mignard produced. So here you have a sample in G magnitude, here you have the number of transits, the number of objects with respect to the number of transits, and here you have the sample in the 10 image axis. So we will have NEAs, we will have MBAs, we will have Trojans, and we will have few TNOs. So for what I have now, it's I have 14,000, almost 40,000 objects, and the total number of observations is almost 2 million. This is an idea on how the validation works. So the idea is that we take only Gaia observations. I've used the orbits from ASDA's website, and I perform an orbit determination using a least square speed and the differential correlations, in which I add the correlation between alpha and delta in each observation. The dynamical model is very precise, and I perform an outlier rejection, which is not the usual one. So it's the usual one, and it takes into account only the random error if the magnitude, the G magnitude is greater than 13. Otherwise, it has to take into account also the systematic error for the bright objects. At the end, what I have are the residuals in alpha and delta, and a long scan and a cross scan. So let me show you the results. This is just one case. This is Eros, and Eros is an NEA, and the magnitude is 14, which means that I've just taken into account the random error. And here you see the residuals in alpha delta. Each symbol represents one transit. So there should be 12 different symbols, more or less. And it had the 53 observations, 2 are rejected, the red points. Here you see the along scan and cross scan, which is the main quality of Gaia. So the residuals are really small along scan, and here you see a zoom around scan. So here we are talking about one mass and the residual of Eros. And here you see these 2 dashed lines represent the 1 sigma level. And then what I've done is that I perform everything on 14,000 asteroids. This is the great result that we have. So what you see are the residual along scan, this line, and across scan. This represents the density of the points we have here. Take into account that each point is an observation. So here we have 2 million of observations. Few cases were discarded, just the 3% of the total. And this is the same in GMAT. So as you can see, the along scan is of course poor if you are going towards higher magnitude. And here you have the problem of the systematics of the bright object, but in the middle is close to 5 mass. And here you see the difference between when we have bright object. That's what happened because we have a 2D window, so we can use the error on a long scan and a cross scan are both useful. So these are the latest results. They are going to be published soon. They will be in the next data release. I really thank you all for your